All right, so good afternoon, everyone. Welcome to the Water and Environmental Engineering seminar this semester. And I'm Ray Lo, Rayson. So I'm a co-chair of the seminar this semester. So today it's our pleasure to invite Professor Joe Scalia as our first speaker in this semester. So Joe is a geoenvironmental engineer and also an associate professor in our department. And his research focuses on the tiling and the mining west, and also groundwater stewardship and some topic in the unsaturated soil. So these topics are strongly related to the environmental and water challenges nowadays. So, and also before Joe joined the CSU, he was an senior associate at the Exponent, which brings the more strong practical perspective to his academic work. So today, Joe gonna give a talk about the tailing management, what it matters, and what is changing. So please join me to welcome the Joe.
Thanks, Ricky. All right, I know some of you. I do not know all of you. Who's undergrad? Master student? PhD student? Professor? Look at Neil didn't raise his hand. Neil just exists at CSU, so it's a different state. So thanks for having me here. I'm going to go through in the next less than an hour a brief overview of why tailings management matters, and then some of what's changing and tie that into ongoing research at CSU and other activities at CSU. And so maybe just to add on at the beginning here, I apologize if I'm lower energy than normal. I've had class the last 2 hours. So this is the third hour of presenting. So we'll see if I can keep pace on all the different topics together and get you excited for this at the end. If I don't, just remember it's still interesting. And so you should think about it on its own merits, not just based on how I present.
We're not gonna cut you any slack, Joe.
No, that's
Top level.
what happened. Let's see. Okay, so some of you in the room, does everybody know what tailings are? Some yeses, some nos. So just to help inform the audience, I decided I would rely on AI. So if you ask AI, what are tailings? Tailings are the material left over after the valuable minerals have been extracted from ore during mining and mineral processing operations. Interestingly, this was the first sentence in a paper I reviewed a week ago. Well, I generated this months ago, so I don't know what that tells you. Maybe this isn't the most engaging version of this. So instead I had it give me a picture. Because everyone likes a picture, right? So this is my prompt, create a 16:9 photo of tailings. And then my chatbot knows that I am in Colorado, and so it's giving me a picture of tailings in Colorado. Not great, but you get the picture, right? We've got finely ground up rock, and we're going to talk about it. So to talk about this, I need to go back first to what generates tailings, which is the mining piece of this story. And so what generates tailings is the extraction of valuable minerals from the earth and then the processing of that extracted material. And so when I say mining, many of you, especially the undergrads, are probably just jumping to this like mining, right? Miners in an underground tunnel. This is in Butte, Montana, not far from where I grew up, mining, right? Or you might think about, here's the Kennecott mill in, what is this, Wrangell St. Ellis National Park in Alaska, where you see old mine infrastructure. And we see a bunch of this in the high country in Colorado. And so we're going to talk first here about mining, although we're not going to talk about that. We're also not going to talk about this, which is, if it's not grown, it's mined, which is really to say that if society relies on something It's either coming to us one of two ways, right? It's grown, agricultural, et cetera, or it's extracted, right? In this case, extracted from the earth. And so those miners in the previous slide were probably trying to get something like this, or maybe not because of the data that photo. Here's some copper. So sometimes when you think about mining, you think about extracting things out of the earth, and we think, oh, we're grabbing these chunks of copper, and then I just turn this into wire, right? But it's more complex than that. Before I get too deep into mining, though, I want to go through a bit more of the backstory to the presentation. And so a bit more of the backstory to the presentation is, among other things, these graphs. Right, and so these are climate data for the United States. This is mean annual temperature across the US from 1901 up until 2020. And you can see the world has not been getting cooler on average across the United States. And so I think this audience, this room probably has a decent amount of comfort that the climate is changing, right? Interestingly, if you try to go to this website now, it's just an archived old website that exists on Internet Archive, but is no longer hosted. No comment on that. And so we're spending a lot of time and effort as a society looking at how do we mitigate climate change and having conversations about the energy transition in varying spaces to varying degrees. Here's a graphic of that energy transition where we're moving from other extractive industries, right? Stored sunlight in the form of coal or oil and gas to maybe nuclear energy. And then we've got mountains with windmills and solar panels in front of them. And so we're just going to have a bunch of wind turbines on the front range, apparently, with solar panels. And we're going to use that to reduce our carbon emissions. And so we could have a much longer conversation about that. But relevant to this presentation, we need increased minerals for clean energy technology as part of the energy transition. And so if we think about some of these conventional methods of transportation, the US is heavily car reliant, right? Conventional car versus an electric car. And so it shouldn't shock you that an electric car requires a lot more minerals for those electric motors, for the batteries for that car, for the charging infrastructure that goes with it. Right, and it shouldn't shock you that these clean energy technologies, say wind or photovoltaic or even nuclear, require more metals as part of their infrastructure than burning. Right, this is something that makes logical sense. And so that's going to be part of the story as it relates to mining. Or maybe we're not going to talk about climate change today, because that's not the in vogue term. And so instead, we'll talk about climate change adaptation. So in this, right, we're adapting to a new climate. And so we're updating our infrastructure. We're adding our solar panels, but we're also hardening what needs to be hardened, building new infrastructure in locations, say, away from current mean sea level as sea levels rise, moving critical infrastructure either underground or away from that burning forest in the background. This is an interesting AI generation of what climate adaptation looks like. Or maybe we should be talking about AI energy use, which weirdly took a bump when I was making this presentation. Total data center electricity consumption, historical, and then future scenarios. And I couldn't find anything more recent than 2023. I'm sure we are on pace for this or exceeding this. And so you see this massive increase in energy consumption, especially for AI specialized servers, as well as conventional servers. And so we've got this huge increase in energy consumption while we're trying to transition away from conventional energy sources. And so that's part of this overall story. And so the outcome of that is there's this huge increase in mineral demand globally. Here we've got lithium indexed to 2020 production levels. And so we see by the year 2040, we just need a 42 time increase in lithium production, which we're already producing a not insignificant amount of lithium across the world, right? Copper, the far end here, right? I only need to double my global copper production in the next 15 years. Oh, and in the US, it typically takes on the order of 25 to 30 years to permit a new mine. Right, so there's a lot to this story. Recycling is part of the story. I'll include it because this is partially an environmental engineering seminar, right? The goal, the hope is by 2030, we can recycle 1% of our metals that we need for this. If we really work at it by 2040, we can get up to 12%. Right, and that's because you don't generate new wind turbines by recycling old wind turbines because there's just not enough of them. Or even more, they don't get a new electric truck by recycling the old electric trucks. There's not a lot of electric trucks out there. We could also have a broader conversation about should we be making electric trucks first before light passenger vehicles or electric bikes, but again, much broader conversation. Another piece of the story that we're going to put together is that where these minerals are being extracted is not where oil and gas has historically come from. And so the graph on the left is extraction of fossil fuels consumed by the United States, and then minerals used by the United States. And so you see oil and gas, we've got a combination of oil that the US is producing with other countries, mainly Saudi Arabia and Russia historically, although that portfolio has shifted. Copper, where's copper coming from? Predominantly massive mines in Chile, right? Where's nickel coming from? Cheap nickel is coming from Indonesia. Where is cobalt coming from? The DRC. Where are rare earths coming from? China. Where are these materials being processed? Almost entirely China, right? And so part of all these concurrent discussions around mining have to do with all these coming together. And so you can imagine in different political environments that different parts of this are going to be more impactful than other parts. And so right now, this part is very impactful, right? From a domestic security lens. But regardless, what we see is we've got an increased global need for mining, and the US currently wants to onshore or move more mining either to the United States or to other countries that are viewed as friendly. Right, and that is not just unique to the US. Saudi Arabia wants to move 1/3 of its economy to metals mining by the 2030s, right, which is a massive increase in mining and mineral processing. So we come back to mining, and we also come back to that the story is a little bit more complex than Sam going out and finding a gold nugget. And you see that in this historic photo, right? Because it's not just someone walking around picking up gold nuggets and no impact. Mining has an environmental impact. It impacts water, right? It impacts air, it impacts humans. Modern mining is not like old-fashioned mining. It has gotten bigger. So this is the Bigham Canyon mine in Utah. And you can see one of the world's largest holes to extract minerals so that we can have an energy transition, so that we can have AI, so that you can have laptops, so that we can stream this presentation live, so that we can have cell phones, et cetera, right? To put just perspective on how large this is, which is not intuitive to me, even if I say this is like a really big hole and you see mountains in the background, but it's still, you know, this could be my kid's sandbox and they're just practicing creating erosion pattern. This could be in the hydraulics lab, right? If we zoom in, here's some of the terraces on the side of that mine. You see these trucks here, right? That's what those look like. These are huge operations to extract the minerals we need for the energy transition, for energy security, for climate adaptation, for building new dorms next to Scott, apparently, right? For all of these uses. Also, interestingly, the mining industry is continuing to change, right? So these trucks shown in this photo, these are electrical mining vehicles in Sweden being used to generate minerals to produce electric vehicles. This is very much a topic of current interest. Here's from a few days ago, House votes for mining near boundary waters in Minnesota. This had been banned in 2023 after a lot of contention around a few different mines in northern Minnesota relating to supplying minerals for the energy transition. And so there's a very wicked problem with where do we mine, who should be impacted, right? Who should bear the consequences of the minerals that the world is relying on. And so that's part of this conversation as well. If we continue to look at mining, and none of you chose, I don't think, mining engineering careers, or you'd be down at Colorado School of Mines, not CSU, studying water and the environment, right? But we've got a really long process that mines is the best in the world for, where you learn about how do you crush the rock into smaller rocks, and then how do you separate it? How do you crush it finer and even finer? And then how do you separate the mineral that you want from the rock? And then how do I take that separated mineral and get it to the point where I can smelt it and turn it into something useful? And there's discipline after discipline, pyrometallurgy, hydrometallurgy, et cetera, into all these processes. And I'm not going to talk about those any further. But mining is really good at turning big rocks into little rocks. And so what you see here is a ball mill, heavy equipment in the background for perspective, rotating at say 20 RPMs, crushing big rocks down into little rocks. And so where my research and where what I'm going to be talking about for the rest of this presentation comes into play is something has to happen to all those crushed up big rocks into little rocks. Some of it goes into copper, which is great, and that's what we wanted, right? Yay. For those nacelles for my wind turbines, for the motors on my electric cars. But if I just look at that copper, I might end up with something that looks like this. This is not AI. This is an artist in South Africa, Dylan Marsh, who likes to create images of the amount of metal that was extracted from this hole relative to the size of the hole. So it's a copper mine. Here's the amount of copper that was extracted from this mine. Where does something else go? Right? And some of you already know the answer to this. It's clearly, I take it and I put it in lava. Does everybody know what this image is from? Where's this image from? This is Minecraft, right? Another use of all that energy that we were just talking about. In Minecraft, you take your waste and it magically goes away. Unfortunately, that doesn't really work. And so instead, we take all of that ground up rock that is now sand or silt-sized particles that's been mixed with a tremendous amount of water to allow all those separation processes to occur. And we need to manage it forever. Right, so that's the tailings piece. The tailings are the tail of that mill process. And here is a picture of a tailings storage facility where we have a slurry being discharged. Slurry is incredibly cheap to transport, right? You just move it down pipes. And so we have solids mixed with water, and we put them behind a dam, and we allow gravity to do its job and get the water back out and keep the solids there, right? And so often the management of this is I build a dam, I deposit material behind it, and then I wait for gravity to do its job, for consolidation to occur. If you've taken geotech, you know consolidation is not a quick process. And then I keep building that dam, and I want to do it as economically as possible, because turns out companies don't like you to say, like, let's spend as much money possible on managing your waste as you can. That's not what they're in the business of doing. But you don't want to spend more money than you have to dispose of trash. If every trash can, you had to give it $1 when you wanted to throw something away, you think you'd be a little bit more careful about what you threw away? Or there'd be a lot more litter in the environment, right? So in tailings, if I have a sand silt-sized particle carried by water, how do I separate those? I deposit it behind a dam, let the particles settle under gravity, I let the water drain under gravity, I continue to stack that up, I build my dam bigger and bigger, I end up with more and more material, I get my water out, that's part of the water story, and I end up with coarser material generally towards the dam side. So this is like the opposite of a water dam, right? It's a dam, but the intent is it tries to get drier and drier through time. And so I build a dam out of sand, and ideally I build the dam out of my mine waste as I go along. And then the finer grained particles get deposited on the far side, right? Which if you study fluids, you understand. And so I have all this really fine material away from the dam, ideally, and that's going to be called my slimes, right? And so then I get to work with this. And so a picture of what that might look like. This is a dam from a copper mine in Chile. This is a 1.3 billion ton capacity dam, billion tons of tailings that are going to go behind it. This has a crest height on this dam of 305 meters. Right, so compare that to, say, the Horsetooth dams that are what, 70 meters high? So 4 times higher, storing waste so that we can have copper. For perspective, here's an aerial version of that. So you can see the dam crest, you can see that sand, you can see that, well, that's tailings, and then you can see more tailings being placed behind it. You can see the particles getting finer and finer as you move away from the dam, and then finally the free water, which gets recycled into the process so it can get reused, because this clearly is, you know, a rainforest. Now, this is high Andes where they're having to pump water up for thousands of meters to get it to the mine in the first place. For perspective, this is CSU's campus. So College, Laurel, Prospect, Shields.
How did you say the dam was, Joe?
This is about 1,000 feet high,
300 meters.
300 meters. So these are huge facilities. Another one of these for scales. Anybody recognize the aerial photo? Salt Lake City. So a tailing storage facility from that mine I showed the picture of earlier. And here's the Salt Lake International Airport. Right, so we're talking about very large structures designed to carry waste and to carry waste forever. The other piece of this is grade of copper ore, but I could plot any number of commodities on here versus time. And what you see is there's a decreasing trend in the grade of ore, meaning we mined all the easy to get copper. And so now we're on to the harder and harder to get copper. And the result of that is when I want a little bit of copper, maybe I get 0.3% by mass copper. So what's the other 99.7% of that mass? It's the tailings mineral solids that then I mix with multiple times its weight in water. Right, so as we need more metal, we generate more mine waste, and that continues on, and it gets worse and worse. So what are some of the challenges in that? Right, you can imagine some of the challenges. We're building mega engineering structures. Right, that in and of itself is not easy. How long is it taking to tear down Glover? Right, and that's about the whole size of the entirety of campus, right? Right, so we've got a large, complex, multidisciplinary system. One of the core challenges in there for the environmental engineers in the room, right, is the chemical stability of that system. So I've designed a material to be reactive. Like inherently, that's what I'm trying to do. I'm trying to grind up the rock so it reacts so I can extract the mineral out of that material. But I've also created something that may react with the environment, and in many cases, if I have sufficient oxygen and sufficient water flux through that system, I can get acid rock drainage. And so one of the challenges here is I need to think about the chemical stability. The other challenge that often lies below this one, like kind of the fundamental, got to get it right or everything else doesn't matter, is I have to get the physical stability right. And so many of you have had one of us show this video of a dam failure. This is an iron ore dam in Brazil in 2019. This is a real-time video. We won't go through the whole thing, but here's the dam in real time.
O terreno todo cedendo e se movendo. E a lama já
Is it the
vai
Brumadinho?
transbordando pela
This is the
margem, vai-
Brumadinho failure. This came only a few years after another large dam failure in Brazil, which had just followed a large dam failure in Canada. There was more than 10 dam failures at tailings facilities last year globally, right? And so these facilities, for a number of challenging reasons, tend to be more complex than water dams. They're built over decades. They're built as cheaply as possible, right? It's waste. A water dam you build all at once and done. And you're generating value, right? You're storing water that is of value. You're generating electricity from hydropower. And so the mining industry has been on this journey of how do I do better with my mine waste management, in particular at a time when mining is now moved from this dirty extractive, right, to being part of the energy transition. And so you've got a lot of drivers here that are pushing the mining industry to do better. And so one of those of late has been the global industry standard for tailings management, which came out in 2020 in response to, among other things, these failures in Brazil, which was brought forward by a group of ICMM, which is a consortium of the largest mining companies in the world, by the UN Environmental Program, and then by the Principles for Responsible Investment, which is an investment arm of a number of large investors, investors like the Church of England, who invest a lot in mining because they're looking for long-term stable industries, for investors like the Saudi Sovereign Wealth Fund, or large capital investors. And so what they've done is they've come together and said, we need to integrate social, environmental, and technical considerations, and we need to have this ultimate goal of zero harm to people and the environment. So the mining industry needs to do this. They can't control the whole mining industry. All they can do is control these big companies that are part of this. But insurance and investors can control the whole mining industry, right? And say, if we're going to invest in you, you need to have this goal of zero harm. And then you've got conflict on, okay, that's great, but it costs money. Do we want to spend money on it? Right? And so the answer is probably, no, I want to spend as little money as possible still, but I don't want a failure, right? Because a failure is unacceptable.
Who issued the standard, Chuck?
Who is what?
Who issued the standard? Was it the ICMM that controls it, or who?
This was issued by ICMM, and it's not a standard. Well, no, this piece is a standard, but it's very, there's a much longer conversation in here on how it gets implemented. And the standard itself is quite high level, and then effectively passes the burden down to, we need good engineers doing good work and meeting a high quality of work generally. And then we also need to be considering in all these decisions, the social aspects, the environmental aspects, what is technically feasible, all of that. But yeah, that's the mining companies in collaboration with these other entities.
Sounds like it's just advisory and nobody's going to really enforce it then.
That's a very interesting question, and a keynote actually soon, which I'll speak to in a moment. So how do we get towards zero harm? One is through good design and implementation. Good design and implementation requires good engineers doing good work, right? That are trained, that are competent, that know best practices, that feel free to disseminate best practices, that allow, folks to talk about case studies, what went wrong, what didn't. And the second piece is technological innovation. And so I'm going to touch on both of those, maybe good practice first. So the first piece of this is there's a lot of these facilities. There's not a global inventory. There's been a few attempts using AI and remote sensing data to try to get at how many of these totally exist. We've tried to take the literature and look at how many of these exist. You get some number above 17,000, maybe closer to 35,000 of these facilities globally. There's a bunch of gray in this map, which we know is not correct. There's mining in a number of these countries, mining in Greenland, though, right? So, and so there's a lot of these facilities, which means if you're going to have good practitioners doing good work, you need a lot of good practitioners doing a lot of good work. The people working on this are predominantly civil engineers, right? And the reason for that is who builds dams, right? Who builds the infrastructure to move this material? Who does earthwork, right? Who deals with directing stormwater away from these facilities? Who deals with erosion on the surface? Who deals with the hydrology of the final cover? Who deals with the groundwater impacts moving off this? A lot of civil engineers, geological engineers, although often that's just serving a redundant, it could be a civil or it could be a geological. Geological has slightly more geology background. some mining engineers that get drawn into it because you can't manage these facilities in the absence of thinking about mining. And then increasingly environmental engineers, although if you think environmental engineers, right, standalone environmental engineering programs that aren't civil engineering programs have not existed for that long. So the civil bucket actually includes a lot of environmentals. And then some geoscientists, some construction managers, construction engineers, and then it goes down from there. So relevant to those in this room. An interesting piece of this then is we need to produce in the next 20 to 25 years the same amount of copper that has been produced through all of human history. And the anticipation is that half the mining workforce is going to retire in the next 6 years. That's just because of ages and that folks are aging out. And so how are you going to dramatically increase production while a big chunk of the workforce is retiring? That's an opportunity. It's a challenge. The graph here is new professional engineering licenses issued in the United States versus time. You see a rather worrisome story here. So pre-COVID, say geotech, which is energy green here, we had maybe 1,300 or 1,200 PEs issued per year. This is for every geotech sector in the country. That has just been decreasing. You see a post-COVID bump. Apparently the geotechs really wanted to take their PEs sooner. The post-COVID bump for water resources and environmental PEs happened a year later. But these numbers are all across the board, 50% down from where they were before COVID and continuing to get worse. What we're seeing the last few years, we're getting the order of 250 new PEs across the entire United States in geotech. Not just tailings, right? That's all geotech. So there's huge opportunity for those that are willing to go through the education and take on the responsibility. So tailings engineers wanted, we don't have enough people working in this space. One of the activities that we spend a lot of time doing at CSU is how do we do recruitment into tailings? How do we do training? And so we're part of a few organizations that do this. We're a founding member of a group called the Tailings Center, which is a university industry collaboration where we're trying to work with Colorado School of Mines and the University of Arizona, who have really great mining and geological engineering programs, but know nothing about tailings. So they make the waste, but they don't think about it. With CSU's program, who cares about the waste, but knows nothing about mining, which is a logical collaboration. And so events like the Tailings Eve that many of you in this room participated in last fall, which we will have another one of this spring, short courses that are for in-person and for industry, or some of those different activities that we work on to try to get people upskilled, to try to steal people from other industries, to try to encourage students like those in the room to think about this as a career choice. CSU also in this, how do we develop mine waste professionals, has hosted the key international gathering for exchange about this information. That's been going on for 47 years. The first Tailings and Mine Waste Conference was hosted as a uranium mill tailings conference in 1978 at the Laurie Student Center. Now it's a larger 1,000-person conference. We share it. We host it every other year, and then it's hosted in Canada. It's heavily industry. There's actually very few students and academics. And these are opportunities where, among other things, Neil, one of the keynotes is going to be how do you enforce that global industry standard on tailings management? So they've stood up a new global tailings management institute that is supposed to be looking at that. And so that's going to be discussed among other topics at the conference. And so part of what CSU does in this space is we try to bring together industry with academia to have conversations about tailings and best practices and how do we all do better, right? Because the only way we do better is if we work together and if we share our failures. And people don't like to share their failures, right? But we learn a lot from sharing our failures. We also do better through technological innovation, right? And so that's the research part of this story. And so I'm just going to highlight a few different areas that CSU is involved in specifically, and then we'll broaden out a little bit to some more generalities, and then I'll wrap up. So one of the ways that we're doing technical innovation is with Celi's project, which is if we want to build better facilities, first we need to understand what is there in existing mine waste or existing facilities, which is more complex than it sounds because many of these were built before we kept good engineering records. Maybe they weren't even built by engineers. And even new facilities, building something and well documenting it all over the world over the course of years is not trivial. Right. And so we spend a lot of time and effort going out and characterizing what exists in the field. And so Celia's project is using something called a cone penetration test, which we go out and we push an instrumented cone into the ground and measure how much force it takes to push that cone and what the pore water pressure is and what the friction is on the side of that cone, shown here in this little excessively large rig. This would be much larger, but you couldn't see it. Pushing its cone, measuring a sounding of what the material characteristics are to figure out, is this material stable and has the water drained down? And potentially then how much water is still going to come out of it and what's the environmental impact of that? Celia is looking at, can we use hyperspectral sensors mounted to those cones plus AI to try to get more information out of this tool? And so we know hyperspectral images tell us information about soils and about mine waste. We know, you can see this, right? You can tell the difference between a dry clay and a wet clay just visually, if you have context, right? The dry versus the wet in these sample photos. Or we can use a hyperspectral sensor to measure a broader range of wavelengths, get a unique hyperspectral signature, and then try to take this and interrogate it, see what information it tells us. And among other things, the questions are, can it tell us the plasticity of that soil? Can it tell us the particle size distribution, the percent sand, the percent silt, the percent clay? Can it tell us the water content? Can it tell us the density? When we add it to those other data streams, can it tell us the density? And so you can see why this is across a large range of wavelengths on a tool that is being pushed into the subsurface that is continually logging data. You very quickly get into a data environment where AI becomes quite useful, and we're trying to do linear regressions would become futile, and Celia would never graduate and she'd be here forever. Right. And so part of research in this area is how do we better understand these existing facilities using interrogative tools, using sensors, using remote sensing? How do we put ORP sensors, Sam, in these facilities to look at the redox, to look at geochemical changes that occur as water drains down, or as we start getting a change in what's occurring in that facility? And so Celia's research is, how do we take these reflectance wavelengths and put them through a convolutional neural network to be able to identify different characteristics, and how much data do we need for doing that? Can we use transfer learning? All sorts of cool technology adaptations for just understanding what's there. And it turns out that actually this, at first blush, works pretty well. Right, so here's 3 graphs: predicted value versus measured value for laboratory measured percent sand, percent clay, and gravimetric moisture content. It's your 1-to-1 plot, so if perfect alignment existed, it would be right on that diagonal line across the plot. So overall, these are doing pretty well compared to other technologies, compared to the uncertainty of these measurements, and that these are geologic scale systems, since they have natural variability, et cetera. So that's one direction of research. Another direction of this technological innovation is thinking about these systems as things that we have built that are going to exist forever. Right, and not just forever, but also climate change. Right, and so how do we think about these big, complex reactive systems and how they're going to exist in perpetuity? And so Saba, who's sitting in the back, is working on a project related to how do we understand the long-term chemical stability of these systems, and then how does that translate to geotechnical and hydraulic characteristics of these materials? So we know soils weather and they evolve, and that changes engineering characteristics. These are reactive systems that are inherently at disequilibrium with the environment when they're constructed. And so the question is, for this wide range of processes, are they potentially physically significant? Under what conditions will they occur? And then should we worry about them? And right now, the way we build a lot of these systems is we build them and we do our characterization for the as-built material. And we think about the failure probability or the potential failure of the as-built system. And that is not the system that is going to exist forever. And so before Saba, we had a student, Heath, who was making pictures and looking at conceptual diagrams of what kind of behavior was happening, looking at different potential failure modes that result from these geochemical transformations. So here's just some water-related failure modes, right? So what's going to happen as the geochemical properties alter the physical characteristics that changes the percolation of water that falls onto these systems, that changes the erodibility. So changing kind of all the different characteristics that could potentially lead to a hydrotechnical failure. Or changes the propensity for internal erosion and piping, which could lead to failure. Right? Or changes the void ratio, which could lead to something that went from dilative to contractive and now could potentially statically liquefy, which is what you saw in that video earlier, but wouldn't have before. So we're looking at these kind of characteristics. Another process here is these tailing storage facilities, all these are designed to do is just wait, right? We're relying on gravity for consolidation to get the water out of these systems. And so what if we want to have this happen faster? How do you get all of the water out of these systems faster? So one of the ways you do that is you squeeze the water out. You don't wait for gravity. You don't wait for self-weight. You put it in a big press and you squeeze it. So here's an example. These are 5 meter by 5 meter screens. This machine exerts the force of a Saturn rocket lifting off to squeeze water out of mine waste. But if you do this, you're able to recover the water, which has value, move it back into the mine waste or into the mining system. And then you also, instead of slurry, end up with something that can be managed much more like soil, that can be compacted to have different engineering characteristics. And so this is called filtered tailings. This is a mine site in the rainforest in a national wildlife refuge in Alaska, where they're using filtered tailings for construction of mine waste facilities. And so we have a number of students who are looking at different aspects of this, abstracts looking at different aspects of this, physicists looking at different aspects of this on how do we build these facilities and how do we scale these up from what's seen here to the size of that big tailings facility, 200,000 tons of mine waste per day. And then you can take it further to say, okay, that's great, but we also have all this rock that needed to be stripped to get to the ore in the first place. And that rock is permeable and reactive, but it's also really strong. And so can we mix those materials together? So maybe we don't need to squeeze as hard and spend as much money or energy to get the water out. Instead, we can blend these together. We can commingle them together to reduce the risk of a physical failure that might exist in the tailings and to geochemically isolate the rock by reducing its permeability and holding onto water, which reduces oxygen ingress that can access that material and build some commingled landform that's going to be more physically stable and more chemically stable. And so we spend time thinking about this. Here's Emily Jagerhorn's boots as an example of what this looks like. So this is 2 rock to 1 tailings at a tailing solids content of 60%. Same tailing solids content, but 1 to 1. Same solids content, but a whole lot more tailings than waste rock. So you can imagine at a landform scale, I want this. It's physically stable. I don't want this slime that's going to move around when I try to drive equipment on it. However, there's a whole bunch of nuance here. Does this actually work? Does it geochemically isolate the waste rock? How do I build this at scale? How do I mix it? How much do I need to mix it? What ratio of rock to tailings is actually viable? So there's a lot of research going on. CSU is involved in research on how do we commingle these materials to build landforms. And all this has gotten so far is these kind of prototype piles looking at small scale, can we do it in the field under natural environmental conditions? But this is far from the size of that tailings dam, right? And so this is a project that we had in Guatemala looking at waste rock and commingled piles and whether or not these are going to have improved physical and chemical stability. There's also an extraction or extrapolation of this that's now underway in Arizona, where they're building bigger piles, trying to look at the physical stability of both filtered tailings and commingled tailings, looking at the erodibility of these materials, looking at the water balance, the geochemistry, and the strength. Because it turns out that building these in and of themselves can be really tricky. Here's an example of building it too wet. It just flows out, right? It looks like the edge of magma running down a hill slope versus building it too dry. Everything segregates on the way down, and they have two separate materials that have very different geochemical characteristics, and the whole thing doesn't go right. So there's a lot of engineering that goes in here, and this is one of the very active research topics for us here at CSU. Last one, we can also reuse this material, right? Which sounds great. Like, let's just get rid of it by reusing it. There's a few problems with this. The biggest problem is making construction materials, like build bricks out of the tailings instead of depositing them in the tailings facility. We can do it, but at the scale that it matters for the magnitude of the problem, it just doesn't work. We don't need that many bricks, and we don't need them in these rural locations where we put mines. We don't build mines in downtown Denver, right? We put them out in the middle of nowhere where society will allow things to be mined. And so one of the other reuse options that's being heavily investigated is this. Mining has historically only gone at a few commodities, and technology has gotten better through time, right? Mining engineers are researching, trying to do better, trying to develop more effective extraction methods. And so we figured that out. And so now the process has become, how do we look at our old mine waste? And the best possible place you could mine would be the old mine waste, right? Because it's already disturbed. It's already been mined. So the first thing you have to do is characterize it. And so University of Arizona is leading a project that we're helping with. How do we identify the valuable minerals in that mine waste? And then once you've identified it, you get into how do you actually extract it? And how do you extract it becomes a big geotech problem, right? Because you need to maintain physical stability while you extract it. And then at the end, you still have, maybe instead of 99% of the material, you have like 99 or 98.9% of the material, right? You still have the vast majority of what was there. So now you need to remanage it again. And there's a lot of other challenges here related to liability, right? Joint and several liability in the United States that once you touch it, it's yours. So who wants to touch a mine waste facility if they don't know what's there to begin with, if there's going to be huge costs? But the federal government is very much interested at the moment in this. How do we remine mine waste to get critical minerals, to get rare earth elements for those domestic security issues? And so one of the areas that we are actively working with lobbyists in the federal government on is how do we reuse mine waste? How do we remine mine waste to both get these minerals, but also ideally take that liability and use modern technology to place it in a configuration that we like a whole lot more than would have existed, say, 70 years ago. And there's a lot of these facilities. Here's a map of mine waste in Colorado. Right, there's been a lot of mining in Colorado. So that's just a sliver of research that we're doing in tailings here at CSU. Generally, a lot of research is being done on this less water, so more filtration question. A lot is being done on sensor-based monitoring, Internet of Things, data assimilation systems, digital twins. How do we use all those tools to build better models? We're thinking more and more about designing for what's going to happen to that facility after it's done. So designing for when it's closed. We're continuing to look for novel technologies. How can we use microbes to help stabilize? How can we use microbes to help remove water quicker or less quickly? How can we turn it into a geopolymer, into stone again, instead of allowing it just to be this potentially geotechnically problematic waste? Generally, the industry is moving towards more stringent standards. Investors, environmental groups are pushing for higher levels of accountability and more care in how this waste is being managed. And so we're seeing collectively this shift towards zero harm. And the way we get there again is a combination of technological innovation and good engineers doing good work, right? So I'll just end with, think about a tailings career. If you're into water, if you're into the environment, if you're into geotech, right? Like, we need more engineers. If you were interested in that, attend some of our Society of Mining, Metallurgy, and Exploration activities at CSU. We have a chapter for a mining professional society at a university that doesn't have mining, which is kind of cool. just to talk about mine waste. Attend one of the Tailings Center Career Eve events that happens later this spring. Take City 555, which is mining geotechnics that Dr. Breither will offer in the fall again. Come talk to me. I'm always happy to talk about mine waste. And with that, thank you for your time.
Thank you, Joe. Thank you
Yeah.
for your great help. So you can have 2 questions.
Neil.
Do you have any cost data on that filtered tailings deal?
Yeah, so filtered tailings is often maybe 5 to 8 times more expensive than slurry tailings management. It still gets used on smaller scale operations currently when there's drivers that make that make sense. You know, if I'm doing something in Alaska in a highly seismic zone in the rainforest, like this is just, it's the only way it's going to happen. One of the big research efforts in that right now is how do you lower that cost? Because you got to get a lot lower, even if it's better for industry to adopt it. So all of these, how do we do better, right? The answer is generally it's going to cost more, right? It's not like we're gonna magically do better. It's not like the engineers that are working in the space are trying to do a poor job. It takes more resources, it takes more technology, it takes more investment. And so one of the pieces, say, talk to the federal government about remining mine waste is you are talking about something that takes away from profit that costs more. Right. And so that's a much more complex story to have.
So 2 questions come up with my mind. The first one is that how do people choose where is gonna be the tailing site? Because supposedly the tailing site should be stable enough, and maybe we don't want too much water over there.
Yep.
But I believe that in the past, people probably just choose the site where it's closer to the mining site
100%.
as
Yep.
possible as they can. But I was wondering if the new standard will have some suggestion for that.
Yeah, so I mean, it's a combination of factors as always, right? You're looking at what's close, so cheaper to move material to. It needs to have the right physical characteristics. You're not going to build something that's utterly unstable. Increasingly, you're looking at what are the other impacts of that facility. On the commingling, for example, I think the first large application of that technology is going to be a mine where for them to expand their existing tailings facility requires taking over entire communities that are existing in adjacent valleys, right? And so the only thing they can do is go up, right? And so there's a lot of factors that go into that hard decision.
Gotcha.
There's a lot of engineering that goes into that. You need to think about the hydrology, right? What's happening with groundwater? Do I have positive groundwater gains, or do I have a losing reach over whatever's there? Can I redirect the flow so I'm not going to get this huge volume of water moving over the top of my tailings facility, causing an overtopping failure, which I absolutely don't want, right? So.
And the second question is kind of a follow-up. So I keep thinking about the comparison between the water dam and the tailing dam.
Yeah.
For water dam, we have we can open the gate whenever the water is approaching the limit, and we can release the water just to make sure it's safe. But for tailing dam, there's no gate that we can release the tailings downstream. So I was wondering there should be a lifespan limit. Like we cannot keep, building up the dam, and when the tailing material just, kept piling up.
I mean, that's exactly the challenge, right? Like a water dam, you realize I have an issue, you drain it, right? In Colorado, where you have to drain it in 5 days. You have to be capable of draining the reservoir in 5 days.
Yeah.
A tailings facility, that doesn't work. And so there's tailings facilities globally right now that they've gone through and done new evaluations and realized the factor of safety is 1.0. Like, they will not even send people onto those to investigate them. They will only send machines because the liability is too high. And so what do you do about that? And so they've gone all the way to building secondary dams downstream in case it fails to catch it. They're in this process in Brazil called decommissioning, decharacterizing, where you take the dam apart and you put it into filtered tailings instead, or into a new dam. So that's a huge challenge. And then the other problem is, unlike a water dam where at the end of life, you just redirect the flow or reach the dam and the problem's gone. right? This, you're not doing that. So you've got a dam that needs to exist forever. And so Canada is dealing with right now, one of the ways they've dealt with their geochemical problems is just, if you want to take the rock and prevent it to react from reacting, you put it underwater. Problem with that is that requires a dam forever, and not just a tailings dam, but also a water dam. And so now what are you going to do with that? That's not the situation. And so if you were thinking about the facility with, I have to manage this forever, how am I going to build this best to manage it forever? That's getting into that, okay, it can only be this big. Okay, it can only be here. Okay, I need to use this more expensive technology. But if you're just thinking about, I'm going to do this as cheaply as possible and not look fully into the future, if that was your constraint, now you have a lot of problems.
Thank you.
Yeah. All right, thanks, everyone. Have a wonderful Wednesday.